How can discovering the hierarchy of tasks with intrinsic motivation enable transfer learning in automatic curriculum learning?
What do I mean by hierarchy of tasks? We can try to consider this kind of setup here, where we have a robotic arm that can play the DJ on a DJ table, interactive table. So he can push and move the blue and red buttons, and with these he can make sounds, and he can also make more sustained music. So these different tasks like moving the end effector, moving the different objects can be seen as hierarchical tasks. You can also have a push around the green objects, and it has to avoid the walls. So you can also see this as a hierarchical task where it can control its own position. And by controlling its own position, it can control positions of green objects. And by controlling this, it can also use it to push other objects around. The idea is how can we use transfer learning to bootstrap the learning of the robot. So the idea is that the traditional supervised learning paradigm breaks down when we do not have sufficient data for the desired task or domain to train a reliable model. And so transfer learning allows us to deal with this scenario by leveraging the data of some related task or domain known as the source task and source domain. And the experience gained in learning to perform one task can help improve learning performance in a related but different task. And so the insight behind transfer learning is that generalization may occur not only within tasks but also across tasks. If we look at how the robot can control its wheels with the sensor data from its LiDAR and other cameras. It can learn a first model to move an object position and use the same raw data to use it to push an object with another. Then there's a relationship between these two, and it can use the first model to transfer the features to the second model, which means that to learn the second model, M2, it can use only a smaller amount of data. So we try to look at how we can use the knowledge acquired from simple tasks to solve more complex tasks or high level of hierarchy tasks. The challenge of multitask learning is that we try to learn the inverse model, so how we can control different features from the environment into joint angles to control the arm position. So mainly we are learning the mapping between the task space to the action space. And in our case, the task space as a total is a composite space, so it's a union of different subtask spaces with different dimensionalities and properties. For the action space, we consider that we can describe action primitives as parameterized functions, pi theta, parameterized policies. But for our action space, we consider that it can be a list of these primitives. So it's a sequence of primitive actions. And a priori, the sequence is not finite. So in the second setup, we have the same kind of problems. We're learning from sensory motor data to command of wheels for the robot. So in both cases, we learn a mapping from a composite continuous space to a space of infinite dimensionality. And the question that I try to solve is how we can learn a mapping between high dimensional spaces and how we can learn all the tasks and in which order, and also how we learn the relationship between tasks so that we can reuse it to bootstrap the learning. So what we proposed is what we call the socially guided intrinsic motivation for a sequence of actions through hierarchical task, which is described by this schema and in detail by this pseudocode. The agent learns by episodes in interaction with the environment. So at the beginning of each episode, it selects a strategy, a task, and a goal to reach. Then it applies this strategy, which translates into a sequence of actions that it executes. And after executing, it observes the outcome, the effect on the environment, and then it computes the competence. And with these competence and these observations, it can both first update the models and its memory to improve its model of the task, but also it can update the outcome and the strategy interest mapping. From this general schema, we implemented two versions. The first is called the SGIM-PB for procedure babbling algorithm, where we consider that the subtasks are already predefined, and so the learner only needs to discover the relationship between the different tasks. And it can also use a teacher to help, so it can also request demonstrations to teachers. In the second implementation, which is called CHIME, we consider that we have different tasks and different observations, but no subtasks have been predefined. So the learner has to discover both the emerging subtask and also how they are linked together. For the first implementation, the SGIM-PB, which stands for Socially Guided Intrinsic Motivation with Procedure Babbling, we consider in our big algorithm that we have two kinds of strategies for learning, either autonomous exploration or imitation. And also the robot can try to explore the policy space, the goal space, but also the combination of sub-goals, so the task decomposition. It can consider sequences of actions as either a sequence of policies directly that are executable by the robot, or it can consider them as a task decomposition that can be translated in fine into policies. The robot needs to map a mapping between the action space and the outcome space, and it can have access to a teacher where the teacher has also an outcome space. To learn, for instance, to make a sound, it should learn that it can use the blue and the green button. So the positions of the green and the blue button will influence the sound that it will make. And so if it knows how to control these buttons, then I can reuse these policies to make sounds. So we can have a sequence of two actions to make one sound. And by observing, for instance, the teacher who shows this other task decomposition, so to make a more complex sound, it can make a basic sound and do something with its hand. Then it can infer that to make a complex sound, it can use a sequence of three actions. And so by composing successively, it can attain sequences of very long actions. So to be able to describe this sequence of actions with this idea of hierarchy of tasks, we propose a framework which is called the procedure framework. So it's a way to represent compound actions in a task-oriented way. And we define a procedure as a succession of outcomes of goals, sub-goals. For instance, here we can consider that combining the positions of the blue and green objects can be decomposed into the first subtask, which is putting the blue object at a position x0, y0. And the second subtask is putting the a green object at position xb, yb. So the task omega 2 is composed of the subtask omega 0 and omega 1. We'll propose algorithms for the robot to learn the associations between goals and procedures, which means that if it has learned such an association to reach the goal B, the robot needs to perform the action sequence A1, A2, where A1 is the policy to reach B1 and A2 is the policy to reach B2. And to discover task hierarchy, then the robot explores the procedure space, and we call this procedure babbling. This is the procedure that is found to associate omega 2 and the procedure omega 0, omega 1. The idea of the algorithm SGIM-PB is that we can learn compound actions using task hierarchy. So to deal with multitask learning, we consider that the policies can be of different complexities. Therefore, we define compound actions as sequences of primitive actions of adapted size. To discover and exploit the task hierarchy, we use task-oriented combination of skills. And to explore, we use both goal babbling, procedure babbling, but also active imitation of several teachers, meaning that the robot can actively request for demonstrations. In the setup that we have an action teacher for the most simple task, omega 0, which is controlling the end effector. So the teacher is showing the policies, the policy parameters for that. And we also have procedural teachers who only show how to decompose different tasks. So for the task for the two objects, for the task to combine different objects and making simple sounds. And for the last task, which is making complex sounds, we don't provide teachers. So we will see how the robot can learn by itself for the most difficult task. So the results of the learning is shown here. So we have the robot that will try to solve the most simple task, which is reaching this point here. This is with our algorithm, so it can go and move the different buttons and then make sound. Sorry. Whereas when we don't have the task decomposition representation, the robot can still go and reach a point. But when we ask it to make a more complex task, it just does something that has nothing to do with the task. It doesn't even it doesn't even know that it needs to do the first step, which it knows how to solve. So if we look at how the robot does it, here we plotted so the number of actions that are used to solve a task. So in blue are the histograms of the policies that it used to solve the control of its end effector. And we can see that most of the time it uses action of 1 or 2 in length. So this is the most simple task, and it uses short actions. And if we look at the other task, let's say the yellow one, which is making a more longer tune, you can see that mostly it uses action of length 5. So it was able to know that this task is more difficult, and therefore it needs more actions before solving the task.
If we look at its internal representation also, this is the histogram of how it decomposes the task omega-1, which is moving the blue robot. And mainly it decomposed it as having a first subgoal, which is moving the end effector, and the second subtask, which is moving the end effector. So mainly it knows that to move an object, it needs first to move its end effector to the initial position of the object and then to the final position of the object. And to make a tune, it needs first to make a small sound and then to push another button to make it sustained. And so this corresponds to what we had designed in the setting, but it didn't know in advance, so it managed to learn it. So our algorithm was able to learn the task hierarchy, and even without the teacher to help. So for the task omega-5, it doesn't have a teacher, whereas for the others, it had a teacher. So even for the task without a teacher, it can manage to learn. If we look at more detail, which strategies it used during its learning phase, we can look at the choices. So these are the histogram of choices of which task it used and which strategy it used to solve each task. So omega-0 is just moving the end effector. It's the most simple task. And it used the action teacher for this task. Whereas the task omega-4, which is making a small sound, it used mainly the teacher for the task omega-4. And this teacher was showing how to decompose the task. So it could spot the right teacher and the kind of demonstration for each task. So for simple tasks, mainly a direct low-level demonstration, whereas for more complex tasks, how to decompose it and so that it can reuse its knowledge. If we look at more broadly, more than the imitation strategies, it can also learn by autonomous exploration, either in the action space or by decomposing the task. We can see that here for the task omega-0, so we said before that it can learn with the imitation teacher 0, but we can see also that it can learn mainly by exploring autonomously the action space. For the task omega-5, which was the most difficult, it doesn't have access to a teacher, so mainly it was doing it by itself. And we can see that it preferred to do task decomposition than to do exploration directly in the policy space. What this says is that it can use mainly policies for simple tasks and procedures, so task decomposition for more complex tasks. If we look at the length of the learning phase, so in the horizontal axis is the number of iterations during its learning phase. We can see that mainly it shows autonomous exploration of policies in the beginning, so this yellow thing. But after that, it switches more to autonomous task decomposition, autonomous procedures. And the same way, all the imitation learning strategies were used in the beginning, and then they were less useful, so he used it less. For the choice of tasks to solve, in the beginning of the learning, it chooses all quite randomly, but mainly the most easy task. So those that are in blue and green. whereas the more difficult task in yellow is chosen a bit later. So it was able to devise its own curriculum for learning, so starting from easy tasks to more complex tasks. So as a conclusion for this part, we have an algorithm that was able to do multitask learning using, and so solve reward sparsity of complex tasks by having an agent that discovers the task hierarchy so that it can use transfer knowledge from easy tasks to complex tasks. We have also algorithm that can do online continual learning in continuous space. And we showed that it's sample efficient and it can devise by itself its curriculum by choosing easy tasks first and then choosing the most adapted teachers for each task. In terms of human demonstrations, it can bootstrap the learning by using procedures for the hierarchical and complex task, whereas it will choose policies for easier tasks. And it can choose what, when, how, and whom to imitate by using the same formula for the reward function that is linked to the progress.
For now, what we've seen is that all the tasks are already given in advance. What happens if the subtasks are not given in advance? How can it discover that these subtasks exist and learn them before completing more complex tasks? So let's come back to this example setup where the robot has to learn how the actions on its wheels will affect the positions of objects that it will push. How can it push an object with another? Well, a simple idea is that before mastering this, it could learn to first control its own position. So generally, in hierarchical learning, you need to learn the features of each of the submodels, but the task of robot position is already given and is already on the list of things that you need to learn. Here we say, okay, we don't know that this is a task to learn. The robot can observe this, but it doesn't know that it needs to learn it and then to reuse it as subtask. So how does it do? Here in our environment, we have, again, actions that can be successions of primitive actions, and each primitive action is a two-dimensional continuous parameters, and it has observables. I can observe where it is, the displacement it has done, and also the positions of the object on the table and the readings of its lidar. The robot explores its environment by episodes in an active manner, and the acquired skills are tested against the test benchmark of all possible outcomes. So we'll try to see if it can move itself in any place in the room, and the objects also, if it can move them in any position in the room. To solve this problem, we propose an algorithm called SGIM for continual hierarchical intrinsically motivated exploration. How does this algorithm work? What does it know in the beginning? So it knows that it can perform primitive actions, like moving the wheels at a given speed. And it can also retrieve the current value of observables, like the position of the robot, the position of different objects, etc. The colors and the physical sizes of objects. So what's the purpose of SGIM? What does it learn? Well, it learns like before, how to achieve a task, to learn the mapping between an effect on or an outcome in the environment and which actions it needs to use to have this effect. It also learns what it can control, what it can achieve, what tasks are there to learn, which are the controllable effects and which controllables are not related to its actions. It also learns the inputs of models. So if there are dependencies or between tasks, for instance, if task 1 is influencing task 2, and effect 1 is influencing an effect 2. For instance, the position of the robot is influencing the position of objects, if it's pushing the object. And so what are the main principles for CHIME to learn? First, it uses intrinsic motivation, like the algorithms before, based on performance progress as an active learning measure to choose what to learn, where to explore, and how to explore. It also uses planning for exploitation. So let me go into a deeper detail about this algorithm. The robot just first selects an affordance and it generates a goal. For instance, an affordance is its own position or the position of an object. Here it tries to reach a position BG that is a coordinate XY, for instance, in the room. And once it has done that, it selects a valid object. So here it's itself, the robot, or it can be for an object A or an object B, a small object or a big object. And then it plans and executes the task. So for that, it needs to use the model of moving the robot. And it will infer a command A, an action A that it sends on its wheels. And when it does that, it moves and reaches a point BR, which is the real outcome or effect on the environment. Then it can, from this data A and B, R, it can update its model of affordance. From that, it can also measure the difference between BR and the goal task, which was BG. And from there, it can have a measure of competence, which is the distance between these two, and update its intrinsic motivation. And then for the next task, it can then either do some random exploration or choose another model or another task. To learn this, it can observe actually its own position and the position of objects. And it tries to relate to its own actions, which is the action primitives of the wheels. So first, it can learn that the wheels relate to its own position. So it creates a first model, which is moving the robot. And when it comes across an object, it can see that it can move the object, and that the position of the object is actually related to the position of the robot. So the model moving an object takes as input the robot position and outputs the object position. And so it learns through these submodels to push an object with another through the commands of its wheels. So this uses a hierarchy of affordances. It also can use affordances multiple times in order to use a sequence of actions. Let's say that, again, it wants to move an object. Then it uses the model moving an object, which uses the model moving the robot. And this outputs a command on an action A on its wheels. And it can reach the object and push it. But what happens if the object is very far? In one time step, it can't reach the object. Then we need to use a planning process. It uses the model of moving the robot several times so that the robot can get nearer and nearer the object to reach it. Here are the results of our experiments when we asked the robot to reach different positions in the room or push the objects into different positions in the room. We have plotted on the x-axis the timeline of learning. And on the y-axis, the task evaluation. So here, 0 means that it's doing bad, and 1 means that it's doing very good. And we can see that for the task of controlling its own position, it learns it quite quickly. And by 300 iterations, so time steps, it has learned to control its own position. The model that it learns says that the robot's position is directly linked to the control of its wheels, but it's also related to the LiDAR reading to detect if there are any obstacles around. The second model, which is controlling position of an object, the model M1, comes in later, around 1000 iterations. And here, the outcome is the object position, and we can see that the inputs is the robot's position. So it learns to link directly the object position to the robot position. And it means that it can reuse the knowledge that it has on controlling the robot position. And it's only later that it learns to push an object with another object. So it creates a new model here, around 1,500 iterations and 2,000 iterations. The learning curve is increasing. So we can see there that through these results, the robot learns multiple tasks. It learns also its curriculum because it starts by mastering its own position, which is a simple task, and it's only at the end that it tries to push an object with another. And it builds the hierarchy between tasks, and it can reuse directly the actions for each subtask to control the bigger task. So last, we'll compare the performance of our algorithm to other methods like Q-learning, deep Q-learning, active-critic, or another algorithm called Curious, which also uses intrinsic motivation. And for the first task, we see that our algorithm learns it quite quickly, around 200, and the other algorithms learn it around 10,000 iterations. So it comes much later. For the second task, which is pushing an object, most algorithms here also learn 15,000 iterations, but we can see that there are a few, like the non-guided Q-learning and deep Q-learning, that cannot perform because their reward functions are too sparse. And on the last task, we see that all algorithms cannot do anything. They cannot learn to push an object with another. And only Curious, which is also another algorithm with intrinsic motivation, can learn, but much later than our algorithm. It learns it around 15,000, 20,000. Chime learns much faster than the other algorithms, and it has a clear advantage, especially for the complex, the high-level hierarchy task. To summarize, Chime could discover tasks, and it can also discover the hierarchy of tasks. It learns to control multiple objects based on physical properties so as to generalize to new objects. It also is a way of using sequences of actions in a manner that is temporally abstract. So there's no clock to tell how long the actions should last. The limits of this approach are still that the sequences of actions are not learned, they are inferred by planning, and it cannot adapt efficiently when a task itself changes yet. Of course, because it uses planning, it might
be having some difficulties when the planning is slow. Therefore, then the SGIM algorithm is also slow. So as a conclusion, I'd like to say that we have presented learning algorithms in various forms for multitask learning, leveraging hierarchy, leveraging discovery of tasks, where we showed that intrinsic motivation, and in particular competence and competence progress, can be used to choose the best transfer of knowledge possible. We have presented SGIM and SGIM that constitute algorithmic framework for learning multiple control tasks through curriculum learning by discovering the dependencies between tasks and exploiting this hierarchy to transfer knowledge from the easy task to the compositional task. In terms of hierarchical reinforcement learning, we have proposed both with SGIM and the procedures, temporal abstractions of sequences of actions. And we showed that our algorithms can learn the discovery of task hierarchy. And that it can use that to transfer knowledge from easy tasks to complex tasks, either through the procedures or task decomposition or planning. In terms of curriculum learning, our algorithms, SGIM, could discover tasks that were not specified to learn in the beginning, and both SGIM and SGIM could choose easy tasks to learn first before tackling more complex tasks. In human demonstrations, imitation learning, we show that demonstrations can bootstrap the learning. And our algorithms can choose the most adapted teachers for each task after learning, understanding their competence domain. Therefore, it can choose between imitation of policy, outcome, or task decomposition or imitation. It can also choose as a whole what, when, how, and whom to imitate. So it can spot who is the best teacher for such task, and also for that task and that teacher, is it better to ask them to give demonstrations of policies, movements, actions, or of task or outcomes, or of task decomposition or procedures. So thank you for your attention. I put the main articles that have been cited in this work.